Hey guys, welcome to lecture 5 of building a RISC-V processor. In this lecture, we're gonna go over the top-level design, the top-level test bench, and how can we put everything together inside the top-level design with the IFU that we built on a previous lecture, and how can we build the instruction decode unit in this particular lecture. So this is pretty much the agenda. We're gonna go over also the instruction memory, how it's built and what it does. This lecture is going to be extremely heavy in code, so make sure to access the code base at the link down in the description, and make sure to hit a like and subscribe to my channel to be notified whenever I upload new lectures. So let's jump into it. Let's jump into the top level design. And the top level design is what instantiates the ICCM, the IFU, the IDU0, the IDU1, the execution unit, and whatever else we need to make our processor work. So let's go right into the code and let's see what this core top looks like. So this is the top level of our, and it has a clock, a reset, and the reset vector. We assume that the top level test bench, which will contain the core top, will initialize those signals. It contains the interfaces, namely the signals that go from one unit to another. And here are the instantiation and the connections between all the units. We will see IDU0 and IDU1 at the end of this lecture, but for now we have the IFU that we built in our previous lecture and the ICCM. Before entering into the details of the ICCM, I just want to give you a quick introduction on what the top level test bench looks like. And this is what it looks like. It has a time scale. It has no input or output ports. It has a clock, reset, and a reset vector inside as signals, and the reset vector is defined in the global SVH file. It instantiates the core top, and we use a dot star notation here because we just have 3 signals to connect at the top. There's no opportunity for confusion. Here we are generating the clock is 100 megahertz clock. That doesn't really matter. And for now, we are waiting 10 clock cycles. We are deasserting the reset signal. And then we wait another 10 clock cycle and we call the finish. As soon as we have the execution unit and we see some real instruction flowing inside our core, we're going to have a more complex finish sequence, and we're going to see that this simulation is going to run until the processor runs out of instructions to run. But for now, we just need that simple finish instructions to close the simulation. And the validator test bench is extremely simple. It instantiates whatever needs to be instantiated and then runs the simulation until the test bench calls the finish system call. So if you want to run this simulation, and this is going to be the command that we're going to use throughout our course, you can make core top sim, and it's going to run the make file, it's going to run validator, and it's going to run the simulation, and it's going to generate the core top BCD, which is our waveform file that we're gonna see at the end of this lecture after we saw each unit. Now we saw the core top, we saw the core top test bench. Let's go into the ICCM because it has some interesting aspects to it. So I've created this mem_lib.sv, and what it contains, for now it contains the ICCM with a depth, a width, and an initialization file that For now, it's a string, it's empty. If you were paying attention, you already saw that I initialized that variable, that parameter, with a file that we're going to see in just a second. Assuming that we initialize it with this file, we don't really need a write port because nobody's going to write into the instruction memory. So we just need a read port for now. And so how big the read address should be. So if we go on the slides, we see that the instruction memory is a byte addressable, word aligned memory. What it means that each address represents a byte and each line is a word. We have 1024 words. Each word contains 4 bytes, so it means we have 4K bytes. We need an address that is able to index 4096, so 4K elements. And what is the relationship here between the parameters that we have here and the size of the read address? Is this one. So we need the logarithm in base 2 of how many bytes we need to address. So the depth is 1024, the width in bit divided by 8 is 4, because a byte is 8 bits. And we have to take the logarithm base 2 of this quantity. How big is this read address? In this particular case, with this combination of depth and width, it's going to be 12 bits. So it's going to be 11 down to 0. We have a read valid in, we have a read data, and a read valid out. So read valid in means that this read address is a valid read address, and so the memory should respond to that read request. We need some internal signals like the memory itself and a line index, a line data. We're going to see why we need this. Why do we need a line index? So the idea of a byte addressable memory, which is not byte aligned, is to first identify the line that contains the byte that we want, and inside that line get the byte that we want. If it's word aligned, how many bytes we have? We have 4 bytes per each line. So this is why if we take the read address and we shift it, in this particular case, we shift it by 2, the line is identified by the shifted value of the read address. So we ditch the first 2 bits that identify the byte, and the upper bits identify the actual line. So suppose that you are in this situation and you are reading, this is byte 3, this is byte 2, this is byte 0 from address 0x000. And then you have the second line of the memory, which is byte 7, byte 6, byte 4, byte 2. What happens if you want to read 32 bits from address 0x002 in this case? So it means that the output should be B5, B4, B3, and B2. But those bytes fall on 2 different lines. If you have a word aligned memory, but you are able to address the bytes, you will always face this issue. And this is an issue both in reading and in writing. Okay, and this is going to be the ultimate reason why we're going to need a queue inside the load and store unit of our processor when dealing with the DCCL, so the data memory. So how do we fix this? Instead of fetching 1 line at a time, we fetch 2 of them and we concatenate them. So here is how the read port works. So line data is concatenation of the line index and the line index plus 1. So we always fetch from the memory the current line and the next line. And the read data is going to be the line data shifted by the bits that we took away from the line index. So for example, here in this case, we discarded the lower 2 bits. Here, we're going to address with those 2 bits. This is basically how you get around having a memory that is aligned to a quantity that is greater than whatever the address index is. We're going to go over this again in very much detail when we're going to deal with the load and store unit, but I just wanted you to put this thing there, and you're going to find some exercises, some resources on the lecture notes inside the repository at the link below for this lecture. So moving forward, let's go and take a look at the instruction fetch unit that we created in the previous lecture. So I've added a few things, a couple things here, but the most important thing that I've added is this instruction memory address valid to know when we are correctly requesting an instruction from the ICCM. So that's pretty much it in terms of ICCM and IFU connection. Let's go now over the decode stage. And if you remember, we divided the decode stage in 2 stages. So instruction decode stage 0 and gets the instruction from the IFU, decodes the instruction by going through the decode tables, generates the control signals for the IDU1 stage and the EXU units, and generates the register file read addresses. So let's go and take a look at how we do it. So this is the IDU. Let's take a look at IDU 0. And we import quite a few things here. We import the global SVH, but also this types.svh, and we're going to see what that file contains. The interface is pretty simple. You have a clock and reset. This is the interface from the IFU. So whatever is an output here is an input here. So we're going to get the instruction valid, and the program counter. The reason why we pass down the program counter is not because we need it, but it makes it much easier to debug things when we're going to start debugging instructions. So if you send the program counter down the pipe, you're going to know exactly when you have a fail what program counter was that instruction. So you can go look back at the code and see, oh, this is what should have been, this is what I get, let's go find the bug. So this is why we're passing down the program counter. On the bonus lecture on the FPGA, we're going to see how this program counter can be removed from synthesis. So when actually synthesizing the processor, because it's going to need it only for debug purposes. Here we have the interface for the next stage, which is IDU 1. And you can see here that this is not a logic, this is a struct. So if we go inside the types, you can see here that you have a struct that contains a type, which is IDU 0 out type. And inside the struct, you have all these signals that get passed down the instruction 1 decode. So what are we passing to instruction 1 decode? We're passing the instruction itself, the program counter value, and again, these are debug signals. We're going to pass the RS1 address, RS2 address that we get from the instruction, the immediate, the destination address, and the shift amount. And we're going to see how we get them from the instruction. And these are all decode signals, and as you can see, those are automatically generated. How do we generate those decode signals that are generated here inside the decode table? So this is the actual decode table. If we take a look at the decode table, this is what it looks like. And this is not manually generated, but it's generated by a script. The file from which we generate this decode table is this one. It's called Decode. And this is a custom encoding. This is something I made up. I actually downloaded it from another core because it had already made the decode table, so I didn't want to remake them. But now I'm going to show you, if you want to remake them, how can you do that. And this is how I encoded the information here. So here you have the instruction definition. The dots are don't cares. Here you have what the input should look like for the decode table, and it's RISC-V instruction, so 32-bit, and this is what you have here, is this thing. Then you have the outputs, and this is the interface that we saw here in types. It's this interface here, and here you have the decode. And what I'm saying is that, let's take the add instruction. What I'm saying is that whenever I have an add instruction, so an instruction comes in, I look at this table and I match this line. I should set to 1 the ALU, the RS1, RS2, RD, PM, ALU signals. Okay, so these are my decode signals, and what the ALU signal tells me is that this instruction needs to go through the ALU. RS1 and RS2 are going to be used as read-enable signals for the register file. RD tells me that this instruction writes back to the register file, and this instruction tells me, this signal tells me that this is an add instruction. Okay, so this is how I encoded information here for the decode tables. Okay, and the way those decode tables are generated is via this script, so dectablegen.py that I've created, and this script takes that file. So here we are parsing the definition, the input, the output, the decode, and the end of the file. So those indexes that you find here. And what the script does, it fetches that file and generates 2 files. And those 2 files are both in Espresso format. Espresso was a tool from the 80s that was used for logic minimization. So you would have a truth table of the most complex functions, and it had a bunch of different algorithms inside to synthesize a logic circuit that implemented that truth table. So this is what Espresso did. You can look at the web page, but in general, Espresso is a software from 1984. It's not around anymore, but a Good Samaritan is maintaining a modern version of it. So this is what we're gonna use for this series of lectures, and you're going to find the instructions to install Espresso here. Okay, very simple, extremely easy to do it. You build Verilator already. This is going to be a cakewalk. So once you got Espresso, you can also install this variable, which is a suite of made by Google for system Verilog development that we're gonna use to basically format the file, the output system Verilog file, to make sure everything is okay with the generated file. So we generate those 2 files. The first file contains the signals that we're gonna put high or not based on the different instruction, and the last file contains the equation for this last signal, which is the legal. You need that legal signal to really qualify whatever you are outputting here. You can send a random combination of 32-bit, and some of the signals will go high, but the legal won't go high. And so this is why we have a separate file for that legal equation down there. So once we generate those two files, we pass them through Espresso. We do some transformation on the output to make sure that the output matches with system Verilog. So for example, the output of Espresso contains an exclamation dot. For the not operation, we know that we have to use a tilde for that. We're gonna clean that up and we're going to generate the system Verilog file. We're gonna pass it through variable Verilog format to get a nice output, nicely formatted. And that's pretty much it. We're gonna create the file. So the nice thing about this is that if you wanna add a new instruction, you can just take the decode file and let's see how we generated the decode for this thing. So if we go here, you can look on the internet for RISC-V green card. And let's take the add. So the first thing we want to look at is the format. The format is R. And this is the same amount of information you have on the previous slides, by the way. So R means that we have a function 7 on RS2, RS1, function 3, RD, and opcode. So if we put this thing side by side with our instruction, you see that where we have RD, RS1, and RS2, we have don't cares because those actually change. Okay, it really depends on the source and destination operands of the instruction. So we are not going to be able to match those to qualify that instruction as an add. But the opcode, the function 3 and function 7, those are going to be specific for the add operation. And to know what those are, you can go on the second page. You can take the add operation and you can see that this is the opcode. So here you have 0110011, 01111. And one secret is that in RISC-V, all instructions that we're going to see will have the bottom 2 bits at 1. Other encodings are reserved like for compressed instructions and whatnot. So add operation opcode 0110011 checks out. Then we have function 3, which is 0000000. And then we have the function 7, which is all zeros. That's pretty much it. You can take a look at the subtract and you can see that the opcode is the same, the function 3 is the same. What it changes is the function 7 with 0, 1, and all zeros. And here you have it. Subtract R, opcode the same, function 3 the same, function 7 has that 1 on the 31st bit. And this is how I built these decode tables here. You can exercise, you can have fun, and like try and delete some instructions and add yours, but that's pretty much how I did it. And you can generate the decode tables with on the top level of our repo with make decodes, and this is going to run that script, and this is how you run it, and this is the output file that we generated. So now our processor is able to decode instructions. Let's see what we do with it. So this is the decode out that goes inside this interface that contains all the signals that we need. So these ones. And then what we do is we start decoding the other operands that we are missing. So for example, RS1 address and RS2 address, which is instruction 19 down to 15 and instruction 24 down to 20. Again, if we take a look at the green card, you can see that RS1, RS2, and RD are same place. Okay, so 19 down to 15, 24 down to 20, and 11 down to 7. So this is the addresses that we have. And this is the immediate. And if you look closely here, I have implemented a mux based on the decode the decode signals that we received from the decode tables. So for example, if the instruction is an immediate, so if the instruction is of this format, so U format, which there are really a couple of those, which is LUI and AUIPC. So LUI is down, should be down here. Yeah. So there's just a couple of those. That's how you want to calculate, how you want to extract the immediate. Otherwise, you have all the other formats that are taken care of in here. So you have 1, 2, 3, 4, 5 prongs of that thing, and then you have 1, 2, 3, 4, 5, 6 instruction encoding. Why do we have only 5? Because one format does not have immediate. Okay, so with those 5 prongs of that multiplexer, we decode the immediate for the 5 immediate instructions. And then we basically pass everything down from the decode table down to the next state with this output flop. Okay, so again, remember that we said that every stage of our pipeline should be flop. This is how we do it. Now, if we go to IDU 1, so the first stage, which is instantiated here at the top level, you can see that IDU 0 out goes into the IDU 1 stage. And if we go into the IDU 1 stage, we can see that we are instantiating the register file, and we're going to see what the register file looks like. And we are asking for the register file with those signals, the RS1, RS2 operands, and these are the read-enabled signals that come from the decode tables. And this is where we get the data then we pass down with the IDU 1 out we pass down the executions. Okay, and as you can see, we pass down the remaining part of the decode signals. Let's take a look at the register file. So the register file has 2 read for RS1 and RS2 and 1 write port that comes from the EXU stage. So the way the register file is, it's like this. So the register file is a logic signal that is attached to a series of flops. We have 32-bit flops. In reality, we just have 31 flops, because if you remember, register 0 is 0, so there's no need to waste a flop to hold 0. Whenever we are accessing that 0 register, in reality we are accessing a wire that is hardwired to 0. So that's pretty much the idea of the register file. And the read enable basically enables the read to the register file, or otherwise we just send 0 down the pipe. Why do we have this read enable? For power. Okay, because here the register file is going to be where you have the most switching going on, and you don't want to fire those line decoders when for each instruction, even for instruction that don't need maybe an RS2. Okay, most of the instruction need an RS1, but RS2 is not really needed. Again, we take that data, we take all the decoding, and then we send it down to the EXU stage, which is going to be next lecture topic. If we go on the top level for a second, you see that here I attached a write back data from the execution unit interface, but for now just floating, it's just hardwired to 0. So again, if we run make core top sim, we let this run and we open up the waveforms. Let's open up the waveforms real quick. And I'm not opening the waveforms with GTK Wave, but I'm opening the waveforms with a new thing that I discovered, which is called Surfer, which is much nicer. It's much faster, much snappier than GTK Wave. So I'll stick to it. I'll put a link on the repo. But you can see here we have the instruction fetch, the instruction decode 0, the instruction decode 1 on the top level, and the ICCM. So this is how we are going to see the things. Again, here you can just click on things and you see all the signals that are going on inside our design. One thing that we can do is we want to make sure that the instructions are flowing down the pipe correctly. So this is the instruction in the fetch stage. Let's go and take a look at the instruction on the decode stage 0 and on the decode stage 1. And you can see that are all spaced by 1 clock cycle. So the pipe is working correctly, and you can see that once the pipeline is full, we have one instruction going in and going out for each clock cycle. At least for now. We're going to see that that's not going to be the case when we start introducing branches. But that's pretty much the idea, and this is where we're going to wrap up this lecture. I just wanted to show you how to generate decode tables, how the core top level and Testbench are assembled, and how can you start playing with the simulation and start seeing things happening. In the next lecture, which is going to be extremely exciting because we're going to wrap up the ALU for this unit, we're going to get the compiler for RISC-V, we're going to attach the golden reference model, which is Whisper, and we're going to modify the Testbench a little bit to generate a log of the instructions that get executed. And we're going to compare the golden reference with our core, and we're going to see if we made some mistakes or not. And we will start running our first ever program on this thing. So this is like the heartbeat test, if this thing is alive or not. So tune in for the next lecture. It's going to be extremely exciting.